All right, so we are going to go ahead and get started. Hello, everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to our webinar today on PFAS Today, Tomorrow, and Forever, Effective Treatment of Forever Chemicals. My name is Maya Bani from the Syracuse University Environmental Finance Center. And just before we begin, we're going to go over a few housekeeping items and then we can get started. During the training today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar questions dialog box anytime throughout the session. We'll be saving most of your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and any other information you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. The session has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the exact webinar date. And if you have any questions or need assistance, please contact smallsystems@syr.edu. And now just a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. And on that note, we can get started. I would like to introduce our presenter today, Will Shaffer, a project engineer from EEC Environmental. And Will, just give me one moment and I'll pass it over to you.
All right. Thank you, Maya. Let me know if we're good to go, if you can see my slides here.
Yep.
All right, if that's the case, then we're off and running. Thank you, everybody, for attending today's webinar on PFAS treatment, our latest installment in this series we're calling PFAS Today, Tomorrow, and Forever. And I'm happy to dive right into this with you. I know this is a topic that a lot of you have been looking forward to hearing about, learning about the treatment technologies available to us on the market today to deal with PFAS. So with that, we'll jump right in. We're going to look at an agenda for today, high level. What we're going to talk about, as always, we're going to have a little bit of a introduction on what PFAS is for those that may be new to PFAS or newer to PFAS, and maybe some terminology around treatment for PFAS as well. Give a little bit, excuse me, of a regulatory overview of where the regulations are at today and where they're heading in the near future. And spoiler, MCLs are around the corner. I know we've been saying that for about a month now, but we'll talk about that. We'll dive into treatment technologies for drinking water and the costs associated with them. I know that's been questions submitted in some of the surveys here for these webinars, is what are the actual costs. So stick around to hear and learn about the costs of treatment for drinking water systems. And then we're going to dive a little bit into what treatment may look like for wastewater systems. And we're going to just touch on destruction technologies just so we can kind of handle start to finish of PFAS treatment. But we're going to do our May webinar is going to be dedicated to a little bit of a deeper dive on destruction technologies. So we're only going to briefly talk about it here today. But with that, we'll get into it, and we're going to go through these intro slides a little bit faster than we have in the previous webinars. Part of the reason is those are available on YouTube. You can go back and read those. So if you want a little bit of a more thorough intro into PFAS, please go back and take a look at those. But an introduction to myself and to EEC. Again, my name is Will Shaffer. I'm a project engineer here at EEC. EEC Environmental is a national consultant. I'm based here in Southern California, as is EEC's headquarters, but we go nationally. We've got a couple offices around the country, a couple people located around the country, and an office on the East Coast as well. And we have a team here dedicated to PFAS, among other things, a team of chemists, engineers, geologists, hydrogeologists, compliance experts, all with that PFAS expertise baked into it, providing kind of full service options for anything and everything related to PFAS, including site assessment, characterization, remediation, wastewater treatment and sampling programs, and local limit development, treatment system design for potable and wastewater systems, industrial pretreatment systems. Then I myself, I've been operating as an owner's rep for a water agency here in Southern California for the last 4 years, kind of tackling everything related to PFAS regulations, where to go. We've now got, this system now has up and running PFAS treatment system for one of their wells. They've got another one nearing completion of construction. We've got another one starting construction, another one being bidded out. So we've gone through this whole process, and I'm happy to share some of the lessons learned along the way with you guys here today. So thanks for joining us. Again, like I said, this is the next installment in a series of webinars that I've been doing for the EFC, and thank you to the EFC for hosting me so that I could talk about this important topic. Like I said, the previous webinars are posted on YouTube. Feel free to go look at those at your leisure. The links are provided here, and you can download the slides from the handouts tab on the GoToWebinar tab there. So feel free to download the slides. The links are there for the YouTube videos. We got the Pearl Jam rear view mirror here. We're looking in the rear view mirror what we've talked about before, but today we're looking forward at what we can do around treatment for PFAS. And with that, we want to intro what PFAS is for some of those who may not be as familiar. Again, this is PFAS is a broad term for a class of chemicals. There are many PFAS constituents within that class of chemicals, over 5,000, depends on who you ask, could be up to 15,000 or more. But it's this fluorinated chemistry that's extremely useful, and therefore it's extremely pervasive in a lot of consumer products. You see down on the bottom here, it's been known or developed with the Teflon line for cookware, nonstick cookware, but its application has been expanded to all sorts of uses, from oil and stain resistance for carpets and clothing to fire retardancy with AFFF, which is aqueous film forming foam for firefighting operations. And the reason it's used in so many products and so many applications is due to the chemistry of PFAS, this carbon fluorine bond, which is extremely stable. It's the strongest bond in organic chemistry, and it provides PFAS chemistry with a lot of this stability that they're known for, and the oil resistance, the stain resistance, the water resistance properties of it. And so it's extremely useful, and it's been used for decades, and that's why we find it so pervasive in the environment as well. A little bit of treatment terminology here that is going to help facilitate this discussion and some of the topics I'm going to talk about. We talk about treatment, PFAS treatment, and what does that really mean? Or PFAS removal. Those terms, treatment and removal, are really general terms that talk about really just taking PFAS out of something. And what does that look like? Well, there's a couple different ways that you can do that. And when you really get down to it, we're talking about separation technologies, when we're talking about treatment technologies for PFAS, really what we're doing is we're separating PFAS from one process stream or one media into another. So we're not altering the chemistry of PFAS per se when we're talking about these separation technologies, and we're going to go into what a lot of those are, examples of those, like GAC or ion exchange or RO. We're not changing the PFAS with those technologies. We're really just separating them from the water column, maybe absorbing them onto a physical media. And then the other kind of technology within PFAS treatment would be concentration technologies. This is where if we're working within a specific media, like within a liquid matrix, water, for example, technology like foam fractionation will pull the PFAS or concentrate the PFAS within that existing media. And so foam fractionation, what it does is it pulls a lot of the PFAS up into a foam on the top of the water. And so we're concentrating that PFAS. You may have a much higher concentration within the foam than you would within the water column. But again, we're not altering the chemistry of that of those PFAS constituents necessarily. And then we're going to talk about destruction technologies. And this is where, when you talk about treatment, a lot of times with different constituents, you're talking about altering that chemistry, you're talking about changing it and removing it. Well, this is where we're talking about actually breaking down PFAS. And when we talk about that, some people use the terminology defluorination. We're breaking that strong carbon-fluorine bond and destroying PFAS. We're not necessarily talking about breaking down carbon-carbon bonds into shorter and shorter chain PFAS. We're talking about the ultimate destruction of PFAS. That may look like thermal destruction or other technologies that we'll talk about at the end here. And then one other term I want to get out in front of is the term pre-treatment. And we're going to use that in a couple different ways here today, primarily in terms of wastewater treatment for PFAS. And you may hear pre-treatment in the industrial world, and that's a treatment system on site at an industry location that pre-treats their wastewater before it heads to the municipal wastewater treatment plant. And that is pre-treatment, that's on-site pre-treatment for an industry. We also use that term when we're talking about that municipal wastewater treatment plant, POTW, which is publicly owned treatment works. We talk about pre-treatment there as well at the POTW, and that's treatment ahead of what we're going to talk about today is PFAS treatment. We can't just treat straight for PFAS at the POTW. There's going to be a number of incremental steps to get there. Those steps we're calling pre-treatment. So with that, we're going to dive right into it here. As always, we're going to talk about what the regulatory environment is, and stay with me. We're getting to the treatment technologies here shortly. Like I said, we'll just breeze through this a little bit faster than normal, but all of this again is coming from the EPA's PFAS strategic roadmap. Again, I encourage you to follow the link here and read through it for yourself and learn about everything that the EPA is doing to address PFAS and all the different regulations, all the different areas that they're developing regulations for: drinking water, wastewater, air, biosolids, all of that. They're doing a lot of work around it. And here's a couple of key markers along the timeline of the strategic roadmap that we're looking at. Today I highlighted, again, early 2024. Here we are, early April 2024. I guess it's still early 2024, where we're looking at the EPA finalizing these MCLs for 6 PFAS constituents. A lot of people believe it's going to happen in the next week or two. I believe Administrator Regan was quoted to say in the next couple of weeks. I saw an article last week where he was saying we plan to finalize these in the next couple of weeks. So we're expecting these MCLs to be adopted any day now. Those MCLs are going to be what drives a lot of public water systems across the nation to put in treatment for PFAS if you're above the MCLs and you got to comply with that MCL. So that's going to be extremely important. That's kind of the first big shoe to drop, if you will. I also highlighted here summer 2024, the EPA says they want to adopt ELGs, effluent limitation guidelines, for a number of key industries known to have PFAS and contribute PFAS to the environment in a myriad of different ways. That is more on the wastewater side of things, and that's going to trigger certain industries to put in pre-treatment of PFAS before they discharge to the municipal treatment plant. So those are two key actions that the EPA is planning to take, two key regulations that would drive the need to put in treatment. So I wanted to highlight those here today, and those are early 2024 and summer 2024, which it'll be here before we know it. Again, UCMR 5, I'm going to talk about this. I just want to highlight this because, again, this is what's going to drive a lot of drinking water systems to put in treatment. And how many drinking water systems are we talking about? That's what we've got here under the UCMR 5 program, and you can go look at one of the previous webinars I did where we took a deeper dive into what that program looks like and what they're doing in that program. But they're sampling for PFAS nationally, the EPA is, and gathering that data. This is data as of January 2024. They put out these data sets quarterly. I expect maybe in the next week for the next data set to drop. I checked this morning. This is still the latest and greatest data. And what we see is of those systems, of those PWSs, public water systems, that have been sampled so far under this program, and you can see almost 2,000 small systems and 1,800 large systems sampled so far. Of the total amount there, I put 17,000 smalls, that's non-transient, non-community systems, and then 4,500 large systems nationally. Of that, we're talking about roughly 15% of all systems nationally have sampling results above the proposed MCLs for PFOA and PFOS. And that's roughly 1 in 10 small systems and 1 in 5 large systems. So again, we haven't sampled everybody. This is what that sampling map looks like, and you can go to the PFAS analytic tools that the EPA has online, and you can generate a map very similar to this. And the brown dots there are the exceedances for PFOA, PFOS above proposed MCLs, soon to be finalized MCLs. And so these would be the systems we would expect to have to put in treatment in order to comply with those MCLs. And then the white dots are the systems that have been sampled thus far in the UCMR 5 program. You're going to see more and more dots populate on this map as they move through that program over the next 2 years. We've gone through 4 quarters of sampling out of 12 quarters of sampling so far. So they're about a third of the way through the UCMR 5 program. Of course, if MCLs are adopted, that's going to require all systems to sample for PFAS within that first year, or after the MCLs are adopted, 4 quarterly sampling events in order to determine conformance with those MCLs. So you're going to see a lot more data come out about PFAS even outside of the UCMR 5 program if and when those MCLs are adopted. And so just a quick recap of what we talked about so far and what's driving the need for treatment. And the next slide is treatment. We're going to talk about drinking water treatment here, but setting the stage here, the strategic roadmap, the EPA's strategic roadmap is kind of what's driving all this regulation. And it's a whole of government approach. They're looking at anything and everything that PFAS could impact and how can we stop those releases of PFAS to the environment within the environmental cycle. So they're looking everywhere. The next one to come is drinking water MCLs any day now. That impact of those drinking water MCLs specifically, we're looking at 1 in 10, 1 in 5 large systems, 1 in 10 small systems nationally are likely to have to put in treatment for PFAS. So it just speaks to the, and you saw that map, it's all across the US, it speaks to the ubiquity of this chemical or this class of chemicals, PFAS chemicals. They're everywhere. Anywhere, it seems like anywhere we look for them, we find them. And then just the need and the immediacy of that is we're looking at those regulations being finalized fairly quickly here. So I always stress to people on these webinars and to my clients, act now. There's no real need to wait here until those regulations are finalized. You can go ahead and start sampling and determine if you've got to deal with PFAS here. Better to know sooner rather than later, in my opinion. So with that, we're going to talk about what treatment looks like for drinking water first, and we'll talk about wastewater as well. So starting with drinking water, since those MCLs will be adopted before too long here. And luckily, and the good news is that there is treatment technologies available to us, mature, established treatment technologies that are effective for PFAS removal, PFAS treatment, PFAS separation, as we said. And this is a great diagram that Corolla put together that kind of talks about the various technologies that are being developed or being looked at for PFAS treatment. And really what you're going to see is we want to be on the right side of this graph, the high efficiency, right? High removal rates, because we've got strict MCLs to comply with. So really we're talking about GAC or ion exchange or RO, nanofiltration. And really what we're going to see on the next slide is those three, GAC, ion exchange, and reverse osmosis, have kind of floated to the top of effective treatments for PFAS for drinking water systems. And we'll talk about some of the reasons why here. GAC, granular activated carbon, is an adsorption technology, as is ion exchange resin. Those two are, and we're going to dive into a little bit more detail as to what those look like. Those would fall under the class of adsorption technologies. They have been around for a long time, used in a lot of different applications in drinking water and wastewater and groundwater remediation. So the good news is they're mature technologies, they're effective, and we know how to use them. And there's a existing market in place if we need to use these for PFAS treatment. Great efficiency. We've demonstrated that across pilot studies, across full-scale implementation studies. They remove specifically to those 6 PFAS constituents that are proposed to be regulated with drinking water MCLs. Very effective treatment down to non-detect levels for those 6 PFAS constituents. So that's great. Those are viable technologies for us that we can implement to comply with MCLs. Pros and cons, kind of weigh those in what we would call an alternatives analysis. Every situation is different, every site is different, every water quality is different, and there's a number of factors that play into that. We're not going to go into all of that today, but I think a couple of ones I can highlight. One is footprint, and I'm here in Southern California. Real estate is expensive. We're fully developed. Footprint is a big driver when we're talking about designing and selecting PFAS treatment options. And so with GAC and ion exchange, both of these are pressure vessel adsorption technologies. The main difference is you're going to have half the number of vessels for ion exchange than you would for GAC. And the reason being is that they have varying empty bed contact times, or the kinetics, the flow through rate through those vessels can flow much faster through ion exchange than granulated activated carbon for the same removal efficiency. And so you can have less vessels for ion exchange and you can have a smaller treatment system. Some of the pros for GAC, though, is that there's a reactivation process you can take advantage of. You may have lower long-term cost if you're looking at a 20 or 30-year lifespan for your cost analysis. So, and there's maybe more of a robust market available that may help tamp down cost escalations when compared to ion exchange, as more and more systems across the nation are putting in these treatment systems. And then we talk about membrane processes, that's reverse osmosis, nanofiltration. So that has been proven to be an effective treatment. It's not even close to as widely spread utilized for PFAS treatment for drinking water systems in particular. And the reason being, one of the primary reasons being, is cost. It's much higher cost than energy cost for RO, but there's also a residual stream, process stream, the reject from the RO process that still has to be managed. With GAC and ion exchange, that PFAS is absorbed onto a physical media that we can dispose of, and offsite. For RO, there's a liquid stream that we have to manage on site, and more so, we can't just be discharging that to the sewer, because that's PFAS laden waste that now becomes the sewer agency's problem. So let's look into a little bit more detail on what those adsorption technologies, like I said, GAC and ion exchange, and I'm going to add into here novel adsorbents. And it's not necessarily important to understand the difference between every type of GAC or every producer of GAC or ion exchange resins or this or that. There's plenty of pilot studies out there that you can look up that have determined the relative effectiveness of each one of these, and looking at the breakthrough curves and how long each one is going to continue to treat for PFAS and what the adsorption capacities are. But I like this visual here so we can kind of wrap our heads around what is the difference between GAC, ion exchange, and then I put into this category novel adsorbents as well. And GAC here, well, before we get into GAC specifically, I guess all three of these are pressure vessel treatment technologies, adsorption technologies that are housed within these pressure vessels. So I like the visual here. If we have to put in treatment, what's that actually going to look like here at the wellhead treatment, or if I've got a centralized treatment system? It's largely these pressure vessels that come in a lead lag configuration. We'll talk about that. These are 12-foot diameter pressure vessels. You can get them smaller for smaller flows as well. Typically, they come packaged like this as a lead lag system that we can install on site. We can pipe to from our well, run through one vessel, then through another. We've got effective treatment at the end of that, and we've got non-detect PFAS water being put into the distribution system at the end of that process. This is kind of what it looks like inside. This is for ion exchange bed here, but it looks very similar for GAC or for novel adsorbents. And you've got source water from your well or from a surface water source coming in the top of the vessel, and then it's being spread evenly and distributed across the top of that bed of media. You can see at the brown layer there is that bed. It's got a resin bed here, that's a carbon bed, GAC bed, and then it flows through that bed evenly. Along the way, it takes advantage of the adsorption capabilities of that ion exchange or GAC or novel adsorbent to attract PFAS, to absorb PFAS onto that physical media, and then through the bottom there, you've got clean water coming out the end with no PFAS, or at least non-detect for the constituents that we're talking about, those 6 that are going to have MCLs. And then we've got a couple of different parts to that. We've got manway access for maintenance. We've got a vent there. But look, by and large, this is what we're talking about. Flow-through technology in a pressurized vessel that takes advantage of that adsorption within the physical media bed here. And for GAC, what does that process look like? Granulated activated carbon. This is usually carbon source. A lot of it is coconut husks that are then activated in a high heat, low oxygen environment. But what it does is the density of pores, and that's why coconut husks and shells are so widely used for this, is they have a ton of tiny little pores within there, a high density of porosity. And that pore space is where the PFAS is adsorbed onto the surface of that GAC particle. And you saw a picture of that in the palm of someone's hand. That's how small we're talking. And then we've got all these adsorption sites on the surface of that particle. And the benefit of having a high porosity density is you actually have a high surface area that the PFAS can absorb to. And that's why it's so widely used. And we're talking about the PFAS molecules are oleophilic. They love oil, and so they're held onto that surface as the water passes through. Similar but different process for ion exchange. You have these ion exchange resin beads, and you saw that in the palm of my hand there, those yellow beads. And what those do is they're charged with, in this case, chloride ions, and you exchange those ions. So PFAS is an anionic exchange process where the PFAS is absorbed onto that resin bead, and then through that process, the chloride is exchanged, and you have this harmless ion being exchanged for this harmful ion. So you get chlorides coming out the end, but you absorb the PFAS molecules onto this resin bead. And then novel adsorbents act very similar to ion exchange. They have very similar kinetics in that we talked about that flow through rate for ion exchange versus carbon being much higher. But the difference here for novel adsorbents is they tend to have greater selectivity, I say here. And what that means is that anionic exchange process, it's not just going to grab PFAS, it's going to grab other competing anions. Well, novel adsorbents are a little more selective to just, or can be a little more selective to just those PFAS anions. And so you may get a greater adsorption capacity for your resin beads or modified clay as opposed to ion exchange, but you still get the same high flow through or the same kinetics that you would for ion exchange, which means half the vessels when compared to GAC. What that typically looks like when we actually apply that, and there's all sorts of details that go into this. Again, we're just talking high level here. If you have an existing groundwater source well or groundwater source, it may be a surface water source like a river or a lake, we'll typically run that through pre-filtration. This may be cartridge filters or sand filtration or bag filters, but some type of pre-filtration. That's just to get the solids out, the coarse solids, in order to protect the media beds within the pressure vessels. And then we're going to run it through this lead lag configuration. This one right here has two different trains, we call them trains, of lead lag pressure vessels. And so you're going to run through the lead vessel, and then that's going to run in series through the lag vessel for redundancy purposes. And then we're out the door here. This one has two trains. You can add 3, 4, 5. And what that does is it just increases the capacity. So you may have one train, 2 vessels for, say, a 700 GPM well. We may have to add a second train if we've got an additional well or a higher capacity well at 1500 GPM. We may end up with 2 trains or 2000 GPM, and then so on and so forth for additional wells. And then what's important to note is through this process, pre-filtration and PFAS treatment, we do have additional losses, pressure losses, head losses through that process. So we may have to end up boosting that at the end in order to overcome the pressure in the distribution system. And then we're going to disinfect on the way into the distribution system. So not super complicated, honestly, when it comes down to it. It's a matter of putting in a couple filters and a couple of pressure vessels, and that's mainly it. I'm oversimplifying it. There's a lot of engineering that goes into that, and a lot of studies that have demonstrated what maybe you want to look at specific media selection as well in that alternatives analysis. But when you get down to it, it's not overly complicated treatment. And then by the end of this process, we end up, or should end up, with non-detect water, potable water going to the distribution system, non-detect for those MCL constituents. What we do is at the end of as we enter the distribution system, we're going to be monitoring there and taking samples to confirm that we have treated effectively for PFAS. What we're also going to do is we're going to sample in between the lead and the lag vessels. And as we do that, what that's going to determine is this concept called breakthrough, right? On the way out, we want to be non-detect. The detection limit, as we discussed in previous webinars, is 2 parts per trillion. The proposed MCLs are 4. Well, that's not a lot of wiggle room between 2 and 4 parts per trillion. And so we want to make sure, that's why we have that lag vessel to provide additional redundant treatment. And then we monitor in the middle there to determine the breakthrough on that lead vessel. And we determine in this case, PFOA concentration. And we graph that along the way. We've got that black line is the lead vessel concentration coming out of the lead vessel. Initially, we're non-detect. It goes down to 0 here, but your detection limit may be 2. And then we start seeing it break through. We start getting detections of 2, 2.2, 2.3 along the way, and we may switch to monthly sampling once we start seeing that breakthrough. And as we approach the MCL of 4, or we may set that a little bit higher, then we're going to change out, that's the red line there. We're going to change out that lead vessel and swap the lead lag configuration. But don't worry, we're still got that lag vessel providing the redundant treatment, and that's the concentration on the blue line going out the door into the distribution system. We're still well below the detection limit there. But this allows us to get the most capacity out of our lead vessel, and then we'll switch that configuration. So there's a lot more to be said about best management practices for that, but in a nutshell, that's adsorption technology treatment for PFAS removal for drinking water. We didn't go into RO again because that's unlikely to be selected for most drinking water systems simply due to cost considerations. And since we're talking about costs, and this was submitted as a feedback on previous webinars, is I never talk about what the actual cost of treatment is going to be. So let's take a quick look at this. I provided the link there to some slides here that talk about these cost curves, or that present these cost curves. I limited it to capital costs, installation costs. They also have O&M costs. And this is a comparison between what the EPA model says the cost for complying with the MCLs is going to be to install treatment. And then Black & Veatch did a study on behalf of the American Water Works Association, AWWA. That's the blue data there, and then there's a smattering of actual real-world case studies as well, and looking at the costs of implementation there. But this gives you a good range. If we're talking about 1 MGD system, which is roughly 700 gallons per minute, you might be looking at somewhere between a cost of 1 to 5 million. I know it's a big range, and it's going to vary regionally across the US as well. But if you're looking at GAC installation for a 1 MGD system, you're looking at anywhere from $1 to $5 million all in to implement treatment. And then you can scale that up at higher flow rates on the right side of the graph on the right side as well. Ion exchange, very similar cost range, actually. If you look again at a 1 MGD 700 GPM system, again, we're looking at anywhere from roughly $1 to $5 million. So you can, if you're looking at and you're asking, well, Will, I have PFAS, we've detected, we've done UCMR5 sampling and we're above proposed MCLs, but really we're only just starting to look at what that means. This is a good way to get a ballpark cost range, and then you can start having those conversations about how you're going to fund these capital improvement projects. And when we talk about funding, I'm going to move to RO here as well and just demonstrate here. You're talking about that same 1 MGD system. We've got a range of what, 1 to 15 million now. So it just demonstrates that higher capital cost for RO, and the O&M costs are even greater as well. When we talk about funding, I'm not going to talk about funding options here today, but I would point you back to the MCL presentation I did for the EFC, where we do explore what some of those funding options are between federal funding and class litigation settlements with 3M and DuPont. So recap of drinking water treatment here. Again, the good news is there are reliable technologies that exist. They're mature technologies. They've been around for decades, mature markets, lots of different vendors that provide similar types of media and pressure vessels and treatment technologies and equipment. That's the good news. They are efficient. They provide treatment down to non-detect levels, so effective treatment that can help you comply with MCLs. The one thing I want to stress is to start planning now. If you're doing UCMR 5 sampling or you're scheduled for it, or once MCLs are adopted, we start sampling and determine if we're above the MCLs. Start planning for what that looks like. Engage a consultant. Come up with an alternatives analysis to find the best value option for you. Start that sampling program. If you have to do piloting as well to find the best value, start that process now. Again, you're going to have 15% of all systems nationally racing to procure this equipment for treatment all around the same time. Once these MCLs are adopted, you got 3 years to comply. So I would stress start now. With that, we're going to talk a bit about what PFAS treatment looks like and may look like for wastewater. I know there's a number of wastewater folks on the line here, and I want you guys to feel the love as well. And the regulations for wastewater, we don't have a federal limit around the corner any day now type of situation. But what we are seeing is a lot of that is driven by drinking water, right? And then as we move through the environmental chain, if you will, that has an effect. So what we've got here is the EPA set health advisory levels for, I'm just looking at PFOA, PFOS here, but 4 other PFAS constituents for PFOA, 4 parts per quadrillion, 0.004 parts per trillion, basically 0. And then for PFOS, 0.02 parts per trillion. Those health advisory levels, HALs, inform the MCLs, the maximum contaminant levels that we're talking about are due to be adopted any day now. Those are proposed at 4 parts per trillion for PFOA, PFOS. But now we got to protect our drinking water source, whether that's a surface water source or groundwater. So we have state water quality standards, water quality standards. And I'm looking at a case study here specifically in Michigan, and you'll see why as we go through the steps here. In the state of Michigan, they've got WQSs for PFOA of 66 and PFOS of 11. And that informs MPES effluent limits at the POTW, again, 66 and 11 parts per trillion. That's the water quality standards that those POTWs have to comply with as they discharge treated effluent from the POTW to these drinking water sources, rivers or lakes. So the plants have to meet that, so then they have to regulate the wastewater sources coming into the plant, and that looks like a local limit. Those are permit limits for industries. And specifically in the Detroit area, Great Lakes Water Authority was the first one to have a local limit in the nation that I know of. They had proposed a total PFAS limit of 7,000 parts per trillion. That was not adopted for various reasons. What was adopted is a local limit of 65 parts per trillion for PFOS for industries. And that helped mitigate influent concentrations into the plant so that they could comply with these MPS effluent limits. And so this is where we're talking about wastewater treatment. You see it in two different spots here. One, the plant dealing with PFAS concentrations and an effluent limit. And then two, industries dealing with what goes out their door and to the plant with local limits. And so it's this industrial side and residential sides. What's coming into the POTW? And does that POTW have a PFAS problem if they're exceeding MPS effluent limits? And then we talked about in a previous webinar, is that PFAS coming from controllable industrial sources that can be mitigated by adopting local limits and enforcing on industries and enforcing them to put in treatment? Or is the majority of your PFAS coming from a residential source that we can't control? We can't have every single household put in PFAS treatment. That's unrealistic. The big problem comes, and this is going to be the case for a number of POTWs across the nation. In fact, it already is, and we're starting to see that. If your main source of PFAS into your POTW is from a residential source, what are we going to do? Again, regulations aren't quite there. This is a little bit of an existential debate at the moment, but I wanted to dive into it a little bit because it's going to inform what we're talking about, what treatment technologies are available for wastewater and why might we use them. And with that, I want to look at what your typical POTW does for treatment. And nationally, a lot of POTWs across the nation have secondary treatment. We have influent coming in, we do primary settling or screening, secondary biological treatment, and then we're out the door. We have effluent water quality standards to comply with, but generally with biological treatment, we can. Maybe in some parts throughout the nation, we have tertiary treatment on top of that because we're producing recycled water for beneficial reuse. Then we talk about what kind of wrench is PFAS going to throw in the spokes here of a POTW treatment train. We talked about GAC, ion exchange, RO as effective PFAS treatment separation technologies. Can we just slap that on the end of the treatment train here at a typical POTW? No. This is that terminology of pre-treatment I was talking about, pre-treatment at the POTW level. What that might end up looking like, and this is the big $100 million question here, is we've got the influent coming in. Again, primary, secondary treatment is kind of our typical POTW. One, we've got PFAS-laden solids being settled out. We've got biosolids coming out of our secondary treatment train. Again, we know those to have PFAS in them. But can we just slap GAC and ion exchange at the end of a secondary level treatment, typical biological treatment? No. We're going to chew through carbon. We got way too many organics in there and other competing constituents. We'd then have to pretty much go through advanced treatment, microfiltration, ultrafiltration, or RO, before we can then polish with GAC or ion exchange in order to meet PFAS effluent limits. And by the time we're done with that, we've pretty much got potable water. And in the arid Southwest here, we're talking about indirect potable reuse, direct potable reuse. We're pretty much talking about going through advanced treatment for direct potable reuse in order to treat for PFAS if we have to treat at a municipal treatment plant. And this is the big problem. And what it's being driven by is, one, those water quality standards. If they're very strict water quality standards that we have to comply with, and we have a residential source that we can't control, this may be the reality for some treatment plants across the nation. And then we've got other regulations coming down the pipe here, CERCLA and RCRA hazardous substances designations, that you see all these PFAS arrows coming out the bottom. We've got PFAS solids and biosolids and RO reject stream and solid media from adsorption technologies. And if those are all designated as hazardous wastes, we'll see what those regulations look like. That's going to be a whole nother problem in and of itself. So this is kind of the existential crisis that the wastewater industry may be facing. We'll see what the regulations look like. There is a way to treat for PFAS at the POTW. It's just extremely expensive and complicated and requires a lot of significant upgrades in order to do so. And that's kind of the point I want to drive home here. Are we looking at POTWs doing this across the nation? Probably not, and certainly not today. But this is the conversation that needs to be started to say, how are we going to comply with these limits? So, recap of wastewater treatment here. Wastewater regulations are coming. If we've got drinking water MCLs being adopted, that's going to start informing water quality standards and MPDS effluent limits that treatment systems are going to have to comply with. In order to comply with that, source identification is going to be extremely important. Like I said, is it residential or is it industrial source? If it's industrial, and we can determine that through collection system sampling and industrial source sampling through our IPP programs, then we can regulate on those industries, reduce our influent loading, and we can achieve compliance at the treatment plant. But if it's a residential problem, uncontrollable problem, that's a whole nother conversation. And if that's the case, that treatment is going to be extremely challenging. Now, we saw all those PFAS arrows coming out of the wastewater treatment plant, and I want to briefly touch on waste destruction because this may be the solution here that we're talking about if we've got a hazardous designation for all of this waste, this PFAS-laden waste. And all the technologies we've been talking about, all these separation technologies, like I said, aren't destroying PFAS, aren't changing PFAS necessarily. You still have PFAS coming out, and it has to be managed. Destruction technologies are emerging and maybe, and are starting to look like they may be the solution, the ultimate solution to PFAS here within the environmental industry. High-level introduction, there are guidances from the EPA and the DoD on what to do with PFAS waste disposal and destruction guidances that we can use to help guide us if we find ourselves in a position where we have a PFAS-laden waste stream that we have to handle and dispose of, whether that's hazardous or not. So I point you to those resources here. The destruction guidance highlighted and linked here is the DoD destruction guidance. And it's a good document. They talk about various disposal and destruction options available for PFAS-laden waste. On the right, we've got an example of what's incineration, thermal destruction. It's available, it's useful and effective, and it's still being demonstrated as to what the ultimate effectiveness of PFAS destruction. And when we talk about destruction, again, we're talking about defluorination, breaking the carbon-fluorine bond. And so we're still demonstrating the effectiveness of that through continually developing additional analytical methods that can help us do these kind of fluorine mass balance to show that we're actually destroying PFAS and breaking that fluorine bond as opposed to breaking it down into shorter chain PFASs. So incineration at a high enough temperature, I think it's 1100 degrees Celsius that we have to achieve to break that carbon fluorine bond, an effective destruction technology. There's also emerging destruction technologies out there that are being developed and piloted and demonstrated: supercritical water oxidation, hydrothermal alkaline treatment, HALT, SQO and HALT, and electrochemical oxidation, among others. Again, these are at pilot scale, some of them other technologies at laboratory scale. Typically, they're low flow, high concentration solutions. So it's not like we can just slap this on at the end of a 2 MGD wastewater treatment plant. That's too high of a flow at current scale. again, they're working on scaling these technologies because the need is so great for PFAS destruction across the nation. I would also point you to this study that was started by the state of Minnesota Environmental Agency, the Pollution Control Agency, that Hazen and Sawyer and Barr Engineering did. Awesome study. It's very lengthy, but very detailed. And it kind of sets the groundwork for what the market is. It was kind of developed as a market analysis, what the market is for PFAS disposal and destruction options as we start putting in drinking water treatment systems and those GAC and ion exchange beds start being exhausted and we have to replace them. We've got this spent media that either needs to be landfilled or needs to be properly disposed of or destroyed. This document does a great job of painting that picture and proposing alternate options to do that, and then explores the idea of how scalable are those, how economically viable are those. And in my opinion, what we might start seeing is, I call them regional PFAS management facilities, maybe CWTs, centralized waste treatment facilities, that may be popping up to meet this demand of all this spent resin media, spent GAC media that needs to be disposed of or destroyed from a PFAS standpoint. And so you may start seeing these facilities pop up accepting that waste and providing that kind of end of the line solution for a lot of systems nationally. So that's the end of my webinar here. I want to highlight a couple of things. One, there is an immediate regulation coming down the line, the drinking water MCLs that are going to start the kind of need for treatment nationally for drinking water in particular. Again, 10 to 20% of public water systems, drinking water systems nationally are likely to require treatment. The good news is that mature treatment options and technologies already exist and can be implemented to provide that level of treatment that's going to be required. Wastewater is a much bigger question. Right now, I would encourage wastewater systems to start the process of source identification to determine what your sources are and if those are manageable sources. That's going to be the easiest option moving forward, is to try to do your source identification and source reduction if possible. And then there is a cost component of all of this. There is a technical assistance component of all of this. There's a lot of information being provided today. There's a lot more details that I didn't go into. I would encourage you to reach out to your local EFC branch within the EFC network and the local rep there, and reach out to them with any questions that you have about PFAS and how you're going to manage this, what you're going to do about it. And they're here to help provide that technical assistance. They can point you to resources in terms of funding options to implement and to fund these projects. And they're going to be a huge resource for you moving forward. So with that, coming to the end of my hour here for the presentation, we want to do a Q&A session here, and I'm going to pass the mic back over to Maya, and hopefully we've got some questions. If you do have questions, please submit them in the chat here, and I'm at your disposal, and I'd love to answer any questions that you got.
Yeah, there's a bunch of questions in the chat here. Will, just in case it's more helpful for you, I sent you a chat message. I don't know if you can see it. It's a bunch of the questions. I just thought it'd be maybe easier for you to understand the questions if you can see them, since there's a lot of acronyms thrown in there.
Sure, I've got 7 questions lined up here. Is that right?
Yeah, that's right. And then I'll add more as they come in. Just, I thought it'd be easier for you to understand the question if you can see it.
All right, yeah. So question number 1, are PFOA, PFOS, PFNA, PFHXS, GenX, and PFBS considered long chain or short chain PFAS chemicals. And those 6 chemicals, those 6 PFAS constituents listed, those are the 6 that have proposed drinking water MCLs. Again, these are specific constituents that are all under that umbrella class of PFAS. And we didn't go into it, but within that class, we kind of talk about short chain versus long chain PFAS chemicals. And what that really is talking about is the chemistry behind it. You have linked carbons in a chain, and then those are fluorinated on either side. And that's the per and polyfluorination of those carbon. And so whether that's a short chain or a long chain of carbons, 3 carbons in a row, 4 carbons, 5, 6, 8. And so each individual PFAS compound, most of those are long chain compounds of 6 carbons or greater. And I'm guessing the reason why we ask is those treatment technologies, GAC and ion exchange, have different demonstrated removal efficiencies, treatment efficiencies for long versus short chain PFAS compounds. The good news is the 6, both GAC and ion exchange, while they have varying short and long chain removal efficiencies, both have been demonstrated to treat all 6 down to non-detect for a good amount of time, a good amount of treatment capacity. You may get anywhere from 12 to 24 months out of a single bed of carbon or ion exchange. And then question number 2, I think there's a typo for GAC. I've read that it may be hard for small systems to get GAC providers to accept small quantities of the used media, which would raise their overall cost. Can you describe what the minimum may be to qualify for reactivation versus just disposing of the used media? So we touched on it a little bit. For GAC, there is a reactivation process where they can strip the PFAS from the GAC, reactivate it, maybe add in a little bit more virgin GAC, and then resource that and recharge vessels with that reactivated carbon. Again, reactivated carbon has been demonstrated to have effective treatment capacity. It's going to be, again, a case-by-case situation. How you got to talk to your vendor and supplier as to how much they'll accept. A lot of those suppliers have what they call muni pools, municipal pools, where they'll accept any amount from municipal sources and pull them all into a single pool so they can take advantage of a scale of economy here and reactivate that entire pool and then source that back out to those municipal clients. So it's going to be case by case. Again, disposing of the media is an option. You got to talk to your local landfills if they'll accept PFAS laden waste. Most non-haz landfills do not accept it due to the potential liability of a CERCLA designation of PFAS, and so you may only be left with hazardous waste landfills as an option, and that's going to be at a higher cost. All of that is a concern, has been voiced as a concern in a lot of the comments in the public comment periods as the EPA has been developing these MCLs, and they're aware that that's going to be potentially a large cost, especially if PFAS is designated as a CERCLA hazardous substance. Question number 3, has the EPA yet to approve the regeneration of GAC for PFAS contaminants? Last I heard from Calgon, they had submitted for approval, but had not heard back from the EPA. Well, again, right now, it's not a regulated compound. There are no official regulations federally for it. So I know that certain carbon vendors are reactivating PFAS laden carbon, and that reactivation process, again, the EPA is looking into it, whether it it is hot enough to actually defluorinate the carbon, or what the waste streams from that reactivation, the gases from that reactivation, what PFAS concentration there are in there. I don't have an official answer for you. I have not heard from the EPA that they've decided one way or another on whether reactivation is going to be viable for GAC once MCLs are adopted, and certainly if and when the EPA makes a determination on CERCLA designation. Number 4, what type of ion exchange is best to use? I talked about you may want to go through this alternatives analysis type of study as you start planning for treatment, and look at the various media types that are available to you. There's a bunch of different ion exchange resins that have demonstrated effective treatment, and there are pilot studies out there. In my backyard here in Orange County, California, the Orange County Water District, OCWD, did and is doing the largest pilot study for PFAS treatment resins and GACs and novel adsorbents, and demonstrating the relative effectiveness of those and the cost effectiveness, basically cost per gallon of those different media. And they've demonstrated a number of ion exchange resins that are cost effective and the relative cost effectiveness of those. The phase 1 study, Evoqua's PSR2 Plus, came out on top as the most effective ion exchange resin. But again, there are other resins, there are novel adsorbents available, and there are carbons available. And it would be best to go through that alternatives analysis and economic analysis for your own specific case. And if you have a very specific water quality on your source, you may even want to go through your own pilot testing before you make these major capital expenditures to make sure you get the best bang for your buck. Question number 5, is there not a waste product for every treatment technology? Backwash water, contaminated resin, and GAC. What happens to the spent resin and GAC? And yes, you're right, there is a waste stream. Again, all of these GAC ion exchange RO, we call them separation technologies, because really we're not treating or destroying PFAS, we're just moving it somewhere else. And so the ultimate treatment, if you will, is the final destruction of PFAS and defluorination of PFAS in order to inert it so it's not a hazardous or toxic substance. And so, yes, with pretty much all of these, there is some type of waste stream to be managed. It's just a matter of how large that waste stream is, what that waste stream is, whether it's liquid or solid, and how you're going to handle that. And the options to handle that are being developed every day, and there's more and more options coming online. Question number 6, what is a BV model? This goes back to those cost curves. BV is just an acronym for Black & Veatch. They're the consultant that did that additional cost analysis on behalf of the AWWA. So those cost curves just have one curve for the EPA's cost analysis, one curve for Black & Veatch's cost analysis, and then those additional black dots are sample size of case studies and actual dollars spent. And then number 7, why was the BV model so much more expensive than the EPA model? There is a report that Black & Veatch authored on behalf of AWWA. I'm sure you can reach out to AWWA to see if you can get a copy of that. That probably speaks to many of the different factors. And then you can also, publicly available is the EPA's cost analysis as they went through the process of developing the MCLs. There's a lot of different factors that go into that, and there's all sorts of arguments one way or the other as to which is correct. Again, you saw a lot of those black dots, those are the case studies. falling somewhere in between those two cost curves. So I would say it just depends on what factors you're looking at, what costs you're looking at. And in every situation, there's going to be a range, and there's going to be a range regionally across the US as well. Question number 8 regarding GAC, are the PFAS removed during the reactivation process, or do they remain in the reactivated carbon? So the reactivation process is a process to strip the PFAS from the carbon. So in theory, and I'm not a GAC expert by any means, but in theory, the reactivated carbon would have limited, if any, PFAS still adsorbed onto the surface of the GAC. And that is kind of backed up by pilot studies that have looked at the treatment capacity of reactivated carbon versus virgin carbon and find a very similar adsorption capacity for PFAS, treatment capacity for PFAS between reactivated and virgin carbon. So that speaks to the reactivation process and the fact that, or the theory that very little of it would be left on the reactivated carbon during that reactivation process. Question number 9, lots of questions here, thank you. Is this possible for large water treatment systems around 200 MGD, as the cost would be really high? What do you recommend for larger systems? Larger systems are going to have larger costs. That's a reality. The other side of that is that costs are shared against a much larger population of customers. Again, I would encourage reaching out to a consultant to go through that alternatives analysis. You may not, for a 200 MGD system, you may not have to treat all 200 million gallons a day. If you have a single source, or if you have multiple sources, you may have non-detect sources. And so you may really only have to treat around 10% of your flow in order to comply with MCLs. If you're 200 MGD and you're far in exceedance of MCLs with a single drinking water source, yeah, you may have extremely high treatment costs to treat a very significant portion of that flow stream in order to comply with those MCLs. If that's the case, I would encourage you to look through that analysis, or have someone go through that analysis to determine what the best value option is for treatment. But if that is the case, if you end up in that worst case scenario, I would also encourage you to start looking at source identification. Try to find that source, remove that source. That would be the most cost-effective option, is if you can protect your source water by removing a contamination source and therefore decreasing your source water concentrations. That's going to decrease the amount of water that you have to treat in order to comply with MCLs. So source identification is going to be huge and be very important for, especially for larger systems that may be facing extremely high costs to comply. Question number 10, PFAS destruction technology. Will this be truly a destruction technology that will not have any long-term negative consequences, or will we realize later in a decade or so that the destruction technology produced another group of contaminants for future times? That's a good question. It's a real concern. I'll point to incineration facilities initially, because of the limited amount of PFAS constituents, terminal compounds that we can quantify through laboratory analysis, whether that's 25 or 40 compounds out of the 15,000. We started doing that analysis at incineration facilities, and we saw high concentrations going in and zero going out for those target compounds, 25, 30, 40 compounds. And we said, look, incineration facilities are destroying PFAS because we have non-detect going out. And what we started finding was actually we may be breaking those longer chain PFASs into shorter chain PFASs, and those shorter chain PFAS compounds are not analytes within our current laboratory analysis methods, and so therefore not captured on the effluent side. And so maybe we're actually just breaking down those carbon-carbon bonds into shorter chain PFASs rather than breaking carbon fluorine. Recently, we have non-targeted laboratory analysis that look at all fluorinated chemistry as kind of a total fluorine mass balance of in versus out. And you see a 99, for many of these destruction technologies, 99.9% removal efficiency of fluorinated chemistry, all fluorinated chemistry, which would include all PFAS. So we have in the last year or two developed analytical methods that allow us to have confidence in these destruction technologies that yes, in fact, we are destroying PFAS and not producing these PIC. In the case of incineration, PICs are products of incomplete combustion. So these shorter chain PFAS compounds are unintended consequences of incomplete destruction. Again, this is an emerging field. We're still learning more and more about it every single day. So maybe we learn something else in a month that changes the script entirely. I don't know. Question number 11 here. Why is PAC not considered a recommended treatment option? It is. I didn't highlight it here. PAC is powdered activated carbon versus granular activated carbon. And PAC has been demonstrated as an effective treatment technology for PFAS. Again, through piloting, you can determine what's going to be the most effective option. If you already have PAC at a drinking water treatment facility, then it's not like you're going to have to add or replace with GAC. You should find effective treatment for the MCL PFAS constituents with PAC. Again, there's all sorts of different technologies, nuances to these various technologies, and I can't highlight all of that in a single webinar. Number 12, is there a particular resin known to be better at removing disinfection byproduct precursors, for example, TOC, at the same time as removing PFAS? Yes, all resins are different, and I would, rather than going into all of it here today, I would encourage you to research some of the publicly available pilot studies that do look at this topic and competitive anions and selectivity of these different resins, and compare that to the water quality of whatever water you're dealing with and determine if they are comparable, if that answers your question, or if maybe you have to do your own individual pilot testing to determine the treatment capacity, adsorption capacity for PFAS for a specific resin or 2 or 3 or 4, while also removing co-contaminants. Got a few more here. 3 more questions. Number 13, has there been testing on sewage biosolids? What additional treatment is foreseen for biosolids? Yes, there has been a number of states that have implemented POTW testing programs, characterization programs that have tested influent, effluent, and biosolids from wastewater treatment plants. And the EPA is working on an influent study right now for many POTWs nationally, a national study. Yes, we have looked at biosolids. Yes, PFAS is present in biosolids. You can see the effects of that if you look at the state of Maine has an outright ban on biosolids applications in the state due to the concern of spreading PFAS through biosolids applications. Treatment options are being developed and evaluated for that. One would be potentially utilizing destruction technologies for biosolids, whether that's raw sludge or produced biosolids, for example, like supercritical water oxidation, treating and destroying PFAS in those biosolids and then producing really just clean water and salts and carbon dioxide at the tail end of that process. That is an extremely emerging sector and emerging technologies to address, in particular, the concern about PFAS in biosolids nationally. Second to last question, do you happen to know which states have higher levels of PFAS in their water systems? I linked the UCMR5 data there and the analytical tools that the EPA has to map that. You can look at the map that I provided to see where the concentrations are. Basically, it's a national issue, and you may see higher levels of PFAS in certain states like California, Michigan, New Hampshire, but these are states that you're only going to see those higher concentrations because they have a lot more sampling data. So there's a sample size bias to that as well, where other states may not have looked at as many drinking water systems, and so you may not have as many higher concentrations because those systems haven't been tested yet. So yeah, I would expect states that have a higher level of industry, in particular industry that is known to contribute PFAS to the environment, like PFAS manufacturers or landfills that have accepted PFAS-laden waste in the past. States that have a higher concentration of those types of industries, you would expect to have higher concentrations of PFAS in their water systems. And then last question, is there a concern that remaining PFAS in reactivated carbon can transfer into water? We kind of addressed this. Yes, the reactivated carbon may have PFAS residuals. In theory, it would not. And we have demonstrated through pilot testing that that does not transfer to the water column. And in particular, that's a big reason why we use this lead lag configuration in these types of treatment systems, so that we have that redundant treatment. So if you have a reactivated lead vessel, and even if there is some pass-through of PFAS from that reactivated carbon, it should be absorbed onto the lag media bed, and you should still have non-detect, and we've demonstrated that through pilot testing that we do still have non-detect at the effluent of reactivated carbon beds. So is that it, Maya? I came to the end of my question list here.
Yep, that looks pretty good to me. I think we're all set to wrap this up.
All right, and if you have any questions that didn't get answered, again, feel free to reach out to the EFC or reach out to me. I put my contact information in there. I'm happy to answer remaining questions that you do still have. So please reach out if you got more questions.
Great. Thank you so much, Will, for sharing your expertise with us as always. For everyone attending, following this webinar, you will receive a follow-up email with the slides from today and a link to the recording. We also ask that you please complete the webinar evaluation following this webinar so you can let us know your thoughts on today's session, as this helps us plan future webinars on topics important to you. Thank you, Will. Thank you all again, and we hope to see you at future EFCN events.
Thank you very much.